Okay, so welcome to the 35th video in the Discrete Structure series. In the last couple of videos, we've been looking into the idea of recursion, recursive definitions, and structural induction. And so we'll be spending two videos, this and the next one, discussing recursive algorithms. And let us see an overview of the algorithms that we're going to study as part of this course. So we'll be starting with the simpler algorithms. The first one that we're going to look at is going to be the factorial. The next algorithm that we'll see is going to be recursive exponentiation to calculate the value of a power n. After that, we'll borrow our idea from the extended Euclidean algorithm to give a recursive definition for a GCD and also implement an algorithm for that GCD. The next algorithm that we'll look at is called modular exponentiation. So this is essentially the task of finding the value of b raised to the power n mod m. We have already seen a non-recursive implementation of modular exponentiation under the topic of binary integer operations. But here we'll be looking at two definitions for b power n mod m, and we'll be giving algorithms for those definitions. And from this point, we'll be moving into a couple of more complicated algorithms. We're going to look at recursive linear and binary search. And finally, we'll be looking at the recursive merge search. And our goal for this video is to cover these four algorithms. And before we start our first algorithm for n factorial, I want to discuss about recursive algorithms in general. So we have already looked into the idea of a recursive definition, and we have already discussed this multiple times, so I'll keep it really short here. So recursive definition contains two parts. The first part would be a base case or multiple base cases if they apply. And there was the actual definition part which told us how to get new elements based on existing elements, or how to compute the values of functions at higher inputs based on the values at lower inputs, how to create new words from an alphabet, how to create new trees from existing trees. So we defined all of those under the recursive step. And for an example function, if we say fn is given by 2 raised to the power n, we described the base case for this function as being f0 is equals to 2 raised to the power 0, and that would be 1. And then we defined the recursive step, which was essentially a way to find new elements. So we just said that the next element n plus 1 would just be the current element times 2. And this is where we stopped. In yesterday's lecture, we diverted a little bit and went on to prove different facts about these recursive definitions, and that was under structural induction. But today, we'll be looking under the implementation aspect of these definitions. If I was asked to calculate 2 raised to the power 5 using this definition, how would I actually carry out that process? So our goal is to give a series of steps that can be followed in order to calculate this using our given definition. For example, imagine that a computer is doing this calculation using this algorithm. The result will not magically appear. The very first thing it needs to do is to check if this exponent is equal to 0. If it finds that the exponent is indeed 0, it can simply refer to the base case and return 1 as the output. But let's say if the input of this exponent is not initially 0, it will have to use this recursive definition and call the same function with a lower input, in our case from 5 to 4. So the idea is that the steps that we talked about, the first step of comparing if the exponent was 0, doing something if it was 0, and doing something else if it was not 0, these steps must be precisely mentioned in order to implement these algorithms and make them useful. So we'll be looking at 4 or 5 different algorithms today. And remember, our goal is going to be to look at these recursive definitions and come up with an equivalent algorithm in order to implement that definition. So with that idea, let's get started with our first algorithm. The first example in my list was for n factorial, but let's do a power n first because this is analogous to the explanation of 2 power 5 over here. So let's get started by forming a recursive definition for a power n. We know it's going to involve a base case and a recursive definition. Now exactly similar to this algorithm, we know that the base case is given by a raised to the power 0, which is equal to 1. And the recursive definition is that in order to calculate the next power n plus 1, and we define it as the previous result, a raised to the power n, multiplied by a one more time. And before we work this algorithm, let me tell you that there are two ways to solve this problem. I can start with my base case and keep deriving new powers away until I reach a raised to the power n. The base case says me a raised to the power 0 is 1. And this definition, if I plug n is equals to 0, gives me a raised to the power 1 is equal to a raised to the power 0 times a. So I know from my base case that this is equal to 1. So a raised to the power 1 will just be equal to a. And if I keep applying this definition successively, I can calculate a squared, a cubed, and all powers away until I reach a raised to the power n. So this type of algorithm that starts on a base case and derives new items until the required item is found is called an iterative algorithm. But on the other hand, if we start working from the highest power of n and keep reducing the problem until we hit the base case, that type of algorithm will be called a recursive algorithm. So a recursive algorithm to calculate 2 power 5 does not start from the base case. It starts directly at 2 raised to the power 5. But then it asks the question, what is 2 raised to the power 5? And it sees that it has to apply this definition. And then this causes it to ask what is 2 raised to the power 4. And you can see how we start from 5 and go all the way to the base case. So that is why it makes it a recursive definition. And repeating one more time, if we started from the base case and kept multiplying by 2 until we reach 2 raised to the power 5, that would be an iterative algorithm. So a recursive algorithm is breaking down a problem, but an iterative algorithm is starting from the base case and building the case that we need. And as a part of this segment of our course, we'll obviously only be looking at the recursive algorithms. So recursive approaches to solve all of these problems. So let me start with a couple of guidelines for designing a recursive algorithm. The first thing that we want to do is to look at the expression that we want to evaluate. And that will tell us what the inputs are. In order to calculate a raised to the power n, I need two inputs. I need a and I need n. And once you have identified the inputs, depending on what your function does, you give it an appropriate name. So we're just going to call this function power. And when we write this algorithm, our very first line is the function signature. So that starts with the function name, power in our case. And just like in a programming language, we list the arguments using commas. So this takes the inputs a and n. So let me say a, and I can add a description if I want. I'm going to say it's non-zero and real number. I'm just keeping it simple. I don't want to hit edge cases like 0 raised to the power 0. And for the power n, we'll not consider negative numbers. So this is going to be non-negative integers. And commonly we mention this is our procedure. Alright, now we know that the first thing that we need to do is to check the exponent n. Because we need to figure out if the base case definition applies or the recursive definition applies. So if the power n that I have received is already 0, I should consider the base case and simply return 1. So let us do that first. We say that if n is equals to 0, let's say then return 1. So this means that if the power is 0, the program terminates at this line itself. And if the power is not 0, this next line will continue. And we know that we need to apply this recursive definition here. And we note even though this definition is given in terms of the next power, remember in this context I need to calculate a raised to the power n. But it's easy to see that a power n is just a raised to the power n minus 1 times a. So if I just replace this n with a n minus 1, I get a raised to the power n is equals to a raised to the power n minus 1 times a. And in fact, I think we could have given this as our recursive definition in the first place. That would have also worked. But either way, the winning thought is to understand that each power is the previous power times a. So let me write that down. And if you are looking at recursive algorithms for the first time, this will be confusing. I'm going to write return. So I need to return a and whatever a raised to the power n minus 1 is. So I'll just mention that by writing a times, and I'll call the same function power with a and n minus 1. And this is enough. And if you do not understand the core idea of recursion, this return statement will definitely be confusing. You should understand that this return can only execute if this value is evaluated. And this value can only be evaluated if this power can be evaluated. So let's say if I start my function with 2 raised to the power 5, a is equal to 2 and n is equal to 5, my procedure will start. It will just skip over this line because the if part is not true and is not equal to 0. So it will try to return. Okay, it doesn't mean return immediately. In order to return, it needs to compute this value, and then it sees that it needs to calculate a. It knows what a is, it is 2. So it knows that it needs to return 2 times something. But what is the other something? We know that the other something is just 2 raised to the power 4. So it is just power of 2 with 4. But what does it mean to write this? It means the same function gets called again with 2 and 4. And when that call reaches this return statement, can it return? It still can return because the fourth power will be defined in terms of the third power. So that means that the function will have to keep calling itself on a stack until it reaches the base case. And finally, when the function gets called with 2 and 0, that is when the function will use the base case and return 1. And once the base case returns, all other functions return in the chain until our calling function returns the final value. Alright, so this being the first algorithm, we took a little bit of time to make sure everything was clear. But the pattern of recursion is going to stay the same for upcoming problems. So we'll not be spending as much time explaining all details. Let's go into our second algorithm. And this time I want to do n factorial. So let us write the definition here. We know the base case. And this time let's name our function here. Why not? We'll just call it fact for factorial. And our base case is going to be the factorial of 0, which is just 0 factorial and equal to 1. And we know the recursive definition for factorial. Factorial of the next term n plus 1 would just be the current term n times n plus 1. But like the last problem, let's define this in terms of n. For our current problem, we'll just say that the factorial of n is just equal to the factorial of n minus 1 times n. And using this base case and this definition, we'll provide our algorithm. So we'll start with procedure. We want to call this fact this time. And what inputs will it take? It will only take one input, and that is n. And for simplicity, we'll just say non-negative integers. Factorial is not defined for negative numbers anyway, but if you are interested, there's something called a gamma function. And the whole idea of factorial is just a special case of the gamma function. And gamma function is defined for all real numbers, but not really relevant to us, so we'll just say non-negative integers. But that apart, what should be the first step? We need to check the value of n to see if we have hit the base case. So we'll just say that if the value of n is 0, we can simply return 1. And if that is not the case, we need to use this recursive definition. That means we need to return the product of n and the factorial of the number 1 less than it. So if this if clause does not execute, we can safely return, we'll return n times the factorial of n minus 1. Next, we'll be looking into the algorithm for GCD of two numbers a and b. And here we'll use the idea of the extended Euclidean algorithm. I'll recall the example that we looked at in the extended Euclidean algorithm. We're looking into the GCD of 84 and 30. And there we established that 84 plus minus 30 times anything would still be a new number that would give the same GCD. Therefore, if I use this pattern to do 84 minus 30 times 2, this gives me 24. And I can add 24 to this list. And now I know that whatever the GCD of 84 and 30 is, the same GCD also applies for 30 and 24. So I've effectively reduced the size of my problem. I was looking at larger numbers 84 and 30. Now I'm just looking at 30 and 24. So even though I'm allowed to find a new number by doing 84 plus minus 30 times anything that I want, I don't want to be completely random. I want to be able to find the smallest value possible so that it simplifies my problem. And the smallest value that I can find, this 24, is simply the remainder of dividing 84 by 30. So when I divide 84 by 30, it's just 30 times 2 plus 24. And you know that we also write this as 84 mod 30. So what is the remainder when you divide 84 by 30? So how does all of this help in making a recursive algorithm? See, now I can give this definition. The GCD of AB is just gonna be the GCD of B mod A and A. And we are saying this based on the assumption that B is greater than A. So A is like my 30, B is like my 84. And remember, our goal is to reduce this to 30 and 24. So B mod A will just be 84 mod 30. That will give me my 24. And the value of A is just 30. So we reduce the numbers 30 and 84 to 24 and 30. And you see the requirement B is greater than A. Since the first number is B mod A, you can say it is definitely less than A because it is the remainder after dividing by A, but the second number is A. So we are still ensuring that the second argument is greater. So whenever our GCD function is called for the first time, we want the larger number to be provided second. And for the subsequent recursive calls, the algorithm will itself ensure that the second number is bigger. And what is the base case for my algorithm? So it is easy to see that the inputs to this GCD function will get smaller and smaller. And between these two inputs, I know that the first one is smaller. And the base case will happen when the first input is a 0. When I encounter that B mod A is 0, that means A exactly divides B. And that is analogous to when we stopped in our Euclidean algorithm. And in that case, the second argument A will be my GCD. So quick recap, we'll just be using these rules to reduce the size of our inputs. Eventually the first input is going to be 0. We'll call that a base case and we'll return the GCD as whatever the second number is. So let's begin by writing GCD of two numbers, A, B. I want these to be non-negative and also ensure that A is less than B. And we know that if the first number is 0, the GCD is the second number. So we can say if A is equals to 0, then return B. And if this is not true, we have looked into this pattern for a couple of times. We just return based on the definition. And it's just going to be the GCD of B mod A and A. Alright, we'll be looking into one more algorithm today. And the last algorithm for the day. This one is modular exponentiation. So we have looked into the theory of modular exponentiation already under binary integer operations. I'll just do a very quick recap, only the parts that is needed for me in this algorithm. So we know that in modular exponentiation, our goal is to be able to calculate b raised to the power n mod m. And in this question, we'll be given a couple of constants. They will tell us m is greater than or equal to 2. n is greater than or equal to 0 and the value of b is between 1 and m. So first we are considering our modulus factor to be greater than or equal to 2, because if we take mod 1 of any integer, we're just gonna get 0. The reason n is chosen positive is because we only want to deal with positive exponents. And finally, the reason b is between 1 and m is because if b is not already between 1 and m, we can bring it between 1 and m. But the process of bringing that between 1 and m is not recursive, and in order to give a recursive definition, we are simply assuming that. But I have mentioned this in our earlier lectures. If we have 10 raised to the power 5 mod 6, we know that this is equal to 10 mod 6. So I can just bring the mod inside, take the power 5 and take the result mod 6. And I know that 10 mod 6 is simply 4. So this will be 4 raised to the power 5 mod 6. So whenever I'm considering b raised to the power n mod m, if my b is greater than m, in this case 10 is greater than 6, I can apply this rule to make sure that b is less than m. And once I get to this stage, this is what I pass into my algorithm. Okay, so these are just conventions that will make our algorithm easier to implement. But we still need to be able to write a recursive definition in order to calculate this. And we'll do that based on this fact. We have this rule in modular arithmetic. Let's say I have the product a times b, and if I'm taking this value mod m, so I can just apply the mod to any of these values. I can say this is equal to a times b mod m, and I can take the whole thing mod m. So this and this will give exactly the same result. But using this property, I have made a recursive definition because modulus is defined in terms of modulus. And let's see specifically the case for b raised to the power n. I can tell that b raised to the power n mod m, and I'll just say this is equal to b raised to the power n minus 1 times b, and this will be mod m. And by applying this rule of product here, I'll give my recursive definition over here. I'll say b raised to the power n mod m. I can say this is just equal to b, and I'll take the second term b raised to the power n minus 1, and I'll take mod m for this one, and I can take the whole thing mod m. And using this definition, the value of n reduces from n to n minus 1. And if I proceed recursively, I'm going to hit the base case. The base case is going to be b raised to the power 0 mod m. And I know b power 0 is just 1. So 1 mod m will simply be 1. When you divide 1 by anything, the remainder will just be 1. So we can definitely use this base case and this recursive definition in order to give an algorithm. But when we actually implement this in practice, we use a slightly different variant of this rule. And if you are asked this in exam, you probably cannot use this rule. There is this improved recursive definition. So we'll provide this definition and use it to form an algorithm. So it uses the same base case, which is b raised to the power 0 mod m, and this is equal to 1. Now in case of the recursive step, so in this definition, regardless of what value of n we get, we just reduce using this expression. But here the case is different if n is even and n is odd. So whenever n is even, we'll use this definition. B raised to the power n mod m is equal to b raised to the power n by 2 mod m squared and then mod m. And then whenever n is given odd, we want to use this rule. B raised to the power n mod m is equal to b raised to the power the floor of n by 2 mod m squared mod m times b mod m and the whole thing mod m. So why this definition works is beyond the scope of our discussion, but we should remember this definition and use it. And we should also understand that using this definition reduces the problem faster. So going over the analytics of these formulas would really take a lot of time, and I think that's unnecessary. So for the purposes of this course, we'll just remember this definition and apply it whenever we need to find modular exponentiation. And understanding the core idea of recursion is always more important. So let's get started with writing this algorithm based on this improved definition. So I want to use this base case and this recursive definition. So I'll just say my procedure and we'll say m power for modular exponentiation. And then we know it takes 3 integers b, n and m, because I need b raised to the power n mod m. And we are given these constants that b is greater than 0, m is greater than or equal to 2, and n is also greater than or equal to 0. Now we know that it is the base case if the power n is 0. It doesn't matter what b and m are, but if I find that n is 0, it is the base case. So I can mention similar to our last examples. I can say that if n is 0, then return 1. So up to this point it is the same. And if you want to apply this definition now, you can directly return this result. I hope you can do that. You'll simply write return b times the m power and you'll just send in b, n and m. And then we reduce the whole result mod m. So it will just be one return statement from this point. So I'll leave this one for you guys and we'll continue with this implementation. This is the more important one anyway. Now if n is not equal to 0, I want to look at two cases. If n is even, then I want to return something. And then I'll write else if n is odd. then I want to return something else. And one quick remark, you could say else if here as well, but after each if we are returning anyway, so the else is not required, and the same thing goes here. But if in your pseudocode you are not returning, you'll want to put the subsequent conditions under else if, so that an unnecessary condition is not checked. So it depends on the algorithm, but in this case, all of this could be if and it would just work the same. So simply the task of returning now, if n is actually even, this is the expression that I want to return, b raised to the power n by 2 mod m squared mod m. So it is just about being able to formulate this using the same function. So this part is my recursion, b power n by 2 mod m. So let me mention that as the call to the same function, m power, and this time I'll be calling with b, n by 2 and m. And now I need to square this value and take mod m. So I'll just square this and say mod m. And in this case, when n is odd, so I need to return this statement, and this is my recursive part. So let me form that first. I want to say m power, and this time I'm calling with b, the floor of n by 2 and m. So I'll just say b, the floor of n by 2 and m. Now I want to square it, mod m, multiply this once again with b mod m, and take the whole thing mod m. It's actually missing here, but I'm taking the whole thing mod m. So I think the only dissatisfying part should be to remember this formula, because in my opinion, I think you'll be expected to give this algorithm if they ask you of recursive modular exponentiation. So that is all the discussion that we'll have for today's video. In the next video, we'll be looking at 3 more recursive algorithms: the linear search, the binary search, and the merge sort algorithm. So I think we'll be finished with this chapter in the next couple of videos. So I'll see you guys tomorrow with the next one. Until then, have a good day and bye.